Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, I want to go over a procedure of finding the domain of composite functions. So I prepared few examples here to go over them, and we will discuss what that entails. So in each one of these examples, we are given two functions. We call them f of x and g of x. And we want to find the composition f composition of g, which means f of g of x. Okay, so find this and identify its domain. So to understand what we are going to do, notice that here we say f of g of x, okay? So the first function we are going to look into is g of x and find its domain. The output of this function is g of x, meaning the range of it, okay? And that will become an input to f. So it has to be in the domain of f. So really, we are going to do two things. First of all, we identify the domain of g of x. Domain of g of x. The domain of g of x, basically here you can see that since we have a fraction, we need to make sure that the denominator doesn't equal 0. So x minus 3 shouldn't be 0, meaning x is not 3. So if I want to write the domain, I can say x is all real numbers except x equals 3, or if you want to write it as an interval, that of course will be a union of two intervals, negative infinity up to 3, and notice 3 cannot be included, right? We don't want it to be 3, so we use a parentheses, union 3 comma infinity. So only the value of 3 doesn't work. Now let's do the composition. F of g of x, what does it mean? Like when you take a function of x, anything, so this is function of g of x. So you go to the g of x function. Notice excuse me, the outer is 1 over x plus 2, 1 over, but every time you see x, you replace it by this thing. Why? Notice that when if I say f of 5, it means every time I see an x, I replace it with 5. G of 2, every time I see an x, I write it 2. X, I write it 2. The difference here is that instead of writing a number, I'm writing a whole function. So this x becomes x over x minus 3 plus 2. Okay, it's really very simple. Every time you see x, you replace it with g of x because it's not f of 5, it's f of g of x. Okay, so now we want to simplify this function. We can use a common denominator by multiplying top and bottom by x minus 3, right? So the numerator becomes x minus 3. When I multiply the first term by x minus 3, I get x plus, and when I multiply the second by x minus 3, I get 2x minus 6. Okay, so here, the domain of this function, notice it inherits the domain of g of x. Okay, because that's the inner one. I cannot enter 3 for g of x, right? So I already excluded 3. So now I can start by saying x doesn't equal 3. And what else? Notice here, I also don't want the denominator to equal 0, but the denominator is 3x minus 6. If I equate it to 0 and solve, I get 3x equals 6 by adding 6 to both sides, and then I divide by 3 and get x equals 2, so x cannot equal 2. Because if it equals 2, then this thing will be infinite, right? 2 divided by 2 minus 3 is 2 divided by -1. It's -2. Plus 2 is 0. So you can see here the domain is negative infinity up to 2, union 2 to 3, union 3 to infinity. And that's the first example. I hope it's clear. We'll take few more examples with different functions so that we can see how it works. Again, I want to find f of g of x, and let's write it f of g of x. So in the beginning, I look at g of x. I want to see the values of x that can go there. If there is anything that doesn't work, I write it down. And then g of x itself, so the value of the function, will go into f as an input, okay? So I want also to see what doesn't work there. What did I want to say? Yeah. Okay. So what we are going to do here is to say that function equals. First of all, we get the domain of G. What do you see here? Every time you have a square root, you want to make sure that the square root is non-negative, meaning x cannot be more than 3. Because if it's more than 3, 3 minus something more than that would be a negative value, and I can't have a real output of a negative square root. So I say here, x has to be less than or equal to 3. Notice it can be 3, because root of 0 is 0. Or if you want to write it, you can say the domain is negative infinity up to 3, and I use a bracket here because the 3 can have the value of 3. Then I construct the composite function f of g of x. So it equals, I have an x. So what do I do instead? I write square root of 3 minus x. And then I square it because it's x squared plus 2. Now, we know that the square and the square root are inverse functions. So when I apply them, they cancel each other, and I get 3 minus x plus 2 equals 5 minus x. 5 minus x is a straight line. It doesn't have any any constraints on the value of x. X can be anything. But remember, we inherited that, so that becomes the domain of the composite function. And you can see for yourself if x is greater than 3, then we said this one doesn't work. But any other value, it's okay. Okay? So if x, as we said, this function doesn't have any constraints to be added to the 3, to negative infinity up to 3, so that stays the domain of this function. So this case is different than the previous one. Okay, the previous one, we had to shrink the domain a little bit by taking another point and excluding it. Again, Here I want also f of g of x. G of x is a polynomial, so it doesn't have any restraint, meaning the domain here is everything x such that x belongs to R, any real value. Or, as we said, we can say it's negative infinity up to infinity. Then we construct the function. Notice f of g of x. So I start with f. It's 1 over, oh, I have an x. So instead of x, I'm going to write x squared plus x minus 3 plus 1, which means it's a ratio. So I want to see what values of x would make the denominator 0. Notice here, I have in negative 2. So how do I get negative 2? It means I can decompose that as x plus 2 times x minus 1, right? You can see two numbers that if I multiply, I get negative 2, and if I add, I get positive 1. So x equals negative 2 would make that 0, and x equals 1 would make it 0. So again, I have a union. I can go from negative infinity up to negative 2, but not including that. Any value between negative 2 and 1, not including the 1, or any value greater than 1. So that these are like 3 intervals in union. Okay? Now, the last one we are going to take, and this one was pretty much easy. Again, we say here that I want f of g of x, the composition of f and g. Now, you have, because g is the inner function, you have to find its domain. I want this value to be non-negative. So the domain is 3 to infinity. If x is any value more than 3 or equal or greater than 3, that's fine. Okay, so now let's go there and see what happens. 1 over 2. Oh, I have x and it's x squared. X is the square root of x minus 3, quantity square, plus 1. Again, I took every x and replaced it by that. And like we said before, the square root and the square cancel each other. So I get 1 over 2x minus 6 plus 1. You distribute the 2, and remember we have an extra 1 here. So it's 1 over 2x minus 5. I don't want 2x minus 5 to equal 0. So 2x minus 5 shouldn't equal 0, meaning 2x should not equal 5, meaning x should not equal 5 halves. But guess what? 5 halves is not part of my domain, right? The domain is from 3 to infinity. This is 2.5. It's like I'm telling you, you know, you can have any value between 3 and infinity, but don't take 2.5. And you say 2.5 is not even from 3 to infinity, so you ignore it. And that stays the domain. Okay, so we looked at different cases. Sometimes the domain will shrink a little bit. Sometimes it stays as itself, or sometimes there was no restriction in the beginning, but then there is a restriction on the composite function. Notice that we could have done the rest the same backwards. So let's take an example. Let's take maybe one of the examples. I don't know which one. Maybe the first one, and try to do g of f of x. Again, it's the same thing. So if I say g of f of x, because f of x is the inner function, I have to find its domain. The domain of f is that x doesn't equal negative 2. Because if it's negative 2, this value would go to infinity. So x doesn't equal negative 2. which you can write it as an interval from negative infinity to negative 2, and then from negative 2 to positive infinity. If I do g of f of x, okay, g of f of x, I have an x, so I replace it by 1 over x plus 2. I have another x, I replace it by 1 over x plus 2, right? And um, minus 3. Like we did last time, I can take a common denominator for the denominator. So the numerator is 1 over x plus 2. The denominator would be negative 3x minus 6 plus 1 over x plus 2. Notice I'm dividing two fractions, so I will get 1 over negative 3x minus 5. Okay, so x here, I don't want negative 3x minus 5 to equal 0, meaning I don't want negative 3x to equals 5, so I don't want x to equal negative 5/3, which is another point that was added to my, or was taken away from my domain. So the domain of the composite function, it's not only negative 2. Notice negative 2 is negative 6/3, so you reach it before that. So you get negative infinity up to negative 2, union negative 2 to negative 5/3, union negative 5/3 to infinity. So you do the exact opposite. Here, remember, we were taking f of g of x. So every time I found x, I replaced it by x over x minus 3. Here I was taking g of f of x. So every time I see an x, I replace it by 1 over x plus 2. And I hope we didn't do anything. No, we didn't do anything wrong. Negative 3x minus 6 plus 1, right? Yeah. So negative 5/3. And that would be the domain of the composite function. I hope this was an easy session. Next time we will try, excuse me, to talk about inverse functions and how can we use the composite function to make sure that two functions are the inverse of each other. Notice inverse, you already know a lot of inverse functions like we did today, the square root and the square, the cube root and the cube, the nth root and the power of n. You looked at the um, trig functions, sine and inverse sine, or arcsine, cosine and arccosine, and so on and so forth. You looked at the logarithm, like natural logarithm and e. These are inverse functions, meaning they cancel the work of each other, and so on and so forth. But what if it was a more sophisticated function? It wasn't something as easy as a square root. It was a function, right? How do I find its inverse? That would be the topic of next time. So stay tuned. Thank you very much for watching and hope to see you soon. Bye.